Hello and welcome. Today we're going to be talking about intermolecular forces. So this is the second part to our last lesson that we were looking at. So let's jump right on in. Okay, so what are intermolecular forces? So these are the forces of attractions between molecules. So once again, if we were kind of looking at what we were doing before, okay, if we had, for example, let's say we had carbon tetrachloride. Okay, and just for simplicity, I'm not going to put all the electrons around it. Okay, but you do know that you need those electrons around the chlorine. Now, what we've been looking at is we've been looking at typically on the inside, the intramolecular bond. Okay, intra means inside. Okay, now, as you guys are aware, typically we're not just going to have one carbon tetrachloride. We're going to have millions upon millions of these compounds whenever we have a solution. So what we're going to try and figure out is, right, if I had a second one here, okay, and I'm just putting a box to show that this is one molecule, this could be another molecule, right, and you get the idea. There's tons of these molecules and they're all intermingling. Now, what's going on between these? And what's going on in between these? And so forth, right? There's an attraction. Are they attracted to each other? Do they repel each other? Do they want to stay close or not? Right? So that's the last part that we're going to be looking at here. And we call this intermolecular forces. Okay? Between molecules and the forces that are in between them. And that's what this here stands for. Okay? So, intermolecular forces. There's forces of attraction between molecules. Now, if there are strong intermolecular forces, it's going to affect our properties. So what this here says, the stronger the intermolecular force means the higher melting and boiling point. Okay? So once again, if I go back to this example here, if these molecules liked each other a lot and they were really close together, it's going to take a lot of energy to break them up. So what that means is that their melting points and boiling points are going to be higher. You need more energy, you need more temperature, more heat to get those particles to break apart. If we have stronger forces or higher forces, most likely that compound's either going to be a solid or a liquid, right? Once again, same idea. If that compound is condensed, it's going to be smaller. It's not going to be far apart like a gas. It's going to be closer in together like a solid or a liquid. And lastly, the stronger the force means the liquid will have a greater surface tension. Now, a surface tension is the energy required to go into a compound. Okay, so for example, it's not the best example, but kind of will give you an idea. If you had a swimming pool of water, okay, if you're trying to put your foot into that water, it's quite easy. Okay, so the surface tension isn't too high. Okay, in retrospect, water does have a high surface tension, but in this example, it doesn't. Okay, what if you had like a swimming pool full of maple syrup? Now, that one would have an even higher surface tension because to try to penetrate that barrier is going to require a lot of strength. So if those molecules are really condensed, it's going to be harder to go through that surface. And that's what we call surface tension. So we're going to look at three different types of forces between molecules. The first one is called a dipole-dipole force. Now, what I'm going to do is I'm going to draw it out so we can kind of get a better idea. Okay, so if we had, let's go HCl, because that's the same example there. So I have HCl. Once again, this is one compound. I have an HCl here. I maybe have an HCl here. Maybe an Cl here. Okay, so I have all these hydrochloric acid molecules and they're all intermingling. And now, HCl, if you go look at your electronegativities, chlorine is stronger than hydrogen. So what that means is that chlorine is going to be delta negative and it's going to make hydrogen delta positive. And the reason why is because that electron movement, right? It's going to pull the electrons towards that chlorine. So it makes chlorine a little bit negative. It makes hydrogen a little bit positive. Same thing over here. Okay, chlorine, a little bit negative, hydrogen a little bit positive, hydrogen's a little bit positive, chlorine's a little bit negative, and so forth, right? We could do that for every single one here. Now, once again, those are called dipoles. Now, what's going to happen is there's going to be an attraction between opposite dipoles. So this negative is attracted to this positive. So there's going to be a little bit of an attraction between these two. There's going to be a little bit of attraction between this positive and this negative side over here. There's going to be an attraction between these molecules, between the positive and the negative side. The positive and the negative side here. So as you can see, there's forces that are going to bring this molecule even closer together. And that is what we call a dipole-dipole force. The dipoles are attracted to other dipoles from this different molecules. And that's what we have here. Okay, so the first one we can have is called dipole-dipole. And this is between two polar molecules. Okay, this only happens between polar molecules because if they don't have these dipoles, then you can't have a dipole-dipole force. So they have to be polar. Now, the more polar a substance is, the stronger the force. So if you had a change of electronegativity of, let's say, I don't know, 0.51, and you had one of 1.60, which ones are going to be stronger? Well, obviously the one with the higher value. Okay, now this is a very strong force. Now, the next type of force that we could have is called a hydrogen bond. Now, this is a type of dipole-dipole force. Okay, this only happens when you have hydrogen bonded to one of these three, nitrogen, fluorine, or oxygen, because these are the three most electronegativity elements. So if you get hydrogen to nitrogen, hydrogen to fluorine, or hydrogen to oxygen bond, one of these three, it's a hydrogen bond. That's what we call this. Okay, now it's a very strong, this is the strongest one. Okay, and this is why water has a high boiling point. Now, it's the exact same idea as your dipole-dipole force. So if you take a look at this compound here, now if you can't see it very well, if you go into your lesson, you'll be able to kind of get a better idea. But here are H2O molecules. Okay, so if I look at this one here, oxygen is delta negative, hydrogens are delta positive, okay, due to its electronegativity values. And it's attracted, same as before. The positive side of the hydrogen is attracted to the negative side of the opposite oxygen. Same thing here, positive to negative, there's an attraction. Positive to the negative, an attraction. So this is a dipole-dipole force. It's just a stronger one. And the reason why it's stronger is because, well, nitrogen, fluorine, and oxygen are your highest values. So it's going to be stronger there. Okay, now what I want to do is I kind of want to make a list for you guys so you guys have a better idea. Okay, now all of these intermolecular forces were created or discovered by a gentleman with the last name van der Waal. Okay, that was his last name. So you may hear the term van der Waal forces because he's credited with coming up with this idea. And essentially van der Waal forces is what we call intermolecular forces. Okay, now there are two main types. Okay, we could have a dipole-dipole force. Now this here has to do with polar molecules. There's also another one that I'm going to talk about right after I talk about this, and it's called London dispersion force. Okay, this happens with non-polar molecules. Okay, now these are the two types. Non-polar, polar, dipole-dipole London dispersion. Once again, it's called London. It's named after the gentleman that came up with that. Now, there's also a different kind of dipole-dipole force, and that's what we call our hydrogen bond. Okay? And once again, this has to do with polar, but more specifically between hydrogen and fluorine, hydrogen and oxygen, or hydrogen with nitrogen. Okay? If it's hydrogen with carbon, it's not a hydrogen bond. It would just be a dipole-dipole if it fell in that category. Okay? So, this is the strongest type of bond. This is number 2, and this is the weakest, or number 3. Okay, so those are the 3 types of bonds, or the types of forces, that we're going to be looking at. Okay, and they're all called intermolecular forces or van der Waals forces, named after the person that came up with that. Okay, so we looked at dipole-dipole, we looked at hydrogen. That should be pretty straightforward. Okay, the last one we're going to look at is called London dispersion. Okay, now these are the weakest intermolecular interactions. Now every single molecule, even polar molecules, will experience it. Okay? However, non-polar molecules will only experience London dispersion. It's not going to experience dipole-dipole or hydrogen bonds. Okay, so what is London dispersion? Okay, so let's say I had 2 molecules, and I'm going to draw some Bohr-Rutherford diagrams. Okay, so this here is for London dispersion. Okay, so I have my protons and neutrons in the middle. Okay, and I have my shells. And in my shells, I have electrons. Okay, it doesn't matter what I have. Okay, same thing here. Protons, neutrons. I have my shells. That's a bad looking shell, but you get the idea. Okay, so I have my electrons on the inside and my valence electrons and so forth. Okay, so I have 2 atoms here. A London dispersion attraction is the attraction between the positive protons to the opposite electrons. Because obviously protons are positive, electrons are negatives. There's an attraction. So these 2 are going to be attracted. They're going to push each other close. Same thing here. Protons on this side, the electrons on that side. So there's going to be an attraction going both ways. Okay? Now, this is a very weak attraction. Okay? This is the weakest one. And on another point that's extremely important, every single molecule, every single compound has London dispersion in it. Okay? The only difference is that when we're looking at our other compounds, dipole-dipole and hydrogen bond are much stronger than this. So if we had a compound, for example, let's say HCl. Okay, let's say we had HCl here. And I asked you, what intermolecular force do we have? Okay, well, in order to do that, you need to figure out that this is a polar molecule, right? This here is delta negative, delta positive, so forth, right? So which forces would be acting upon it? Okay, yes, London dispersion. London dispersion acts on everything. But we also have a dipole-dipole force. So on a test or assignment, if I ever asked you which intermolecular force is present, I am looking for the strongest one. So you wouldn't tell me London dispersion, you would tell me dipole-dipole. Okay, same idea. Let's say I had H2O. Okay, H2O, we have that oxygen to hydrogen bond. So we would have, what forces would we have here? We would have London dispersion. I'm just going to put LD. We would have dipole-dipole. We would also have a hydrogen bond. However, which one is the strongest? Well, hydrogen bond is. So we would not say that one, we would not say this one, we would say just hydrogen bond, even though these ones are present there. Okay, so when being asked a question like this, that's what I'm looking for here. All right, what we're gonna do before we move on to our last page, we're gonna do one example, okay? And we're gonna do an example like our last lesson with all the different steps. And this time we're gonna do a little bit trickier one. We're gonna try, let's see, which one can we do? Let's try sulfate. Okay, sulfate is SO4, 2 negative. Okay, that should, I'm trying to think of this in my head. It should work, okay? So, let's go ahead and let's try this out. So for number 1, we need to draw our compound. Okay, so we do this by drawing sulfur. So sulfur has 6, 1, 2, 3, 4, 5, 6, and it has 4 oxygens. So we're going to need to, once again, like we did in previous lessons, we're going to have to break up these bonds. So I'm going to put an oxygen at the top. Oxygen has 6. Oxygen has 6. Oxygen has 6. And so forth. Okay, so now we're going to have to play around with this a little bit. Okay, I'm hoping this works here. Okay, now the first thing we need to do is we need to break up all these bonds. Okay, so every single one on the outside needs to be connected on the inside. So I see one here. I see another here. We're going to have to break up this bond here, unfortunately. And we're going to have to break up another bond here as well. All right, now we're going to have to kind of rearrange a couple things here. So the first thing I see is that I have 2 negative. So I'm going to add 2 electrons, and I'm going to add it in the spots where we can't move electrons. So we can move these 2 electrons. We can't move any here. So I'm going to put 1 electron there and 1 electron there. Those are the 2 I'm adding in. And then from previous lessons, you guys remember that we can take these electrons and move spots. So I'm going to take this electron and move this one here. And I'm going to take this electron and move it there. So what I have now is I'm going to have this compound. I'm going to have sulfur to 1 oxygen, to a 2nd oxygen, a 3rd oxygen, a 4th oxygen. And each of these oxygens are going to have 1, 2, 3, 4, 5, 6, all the way around each one. Now, once again, because this is a polyatomic ion, I need my square brackets, and I need my charge, which is a 2 negative charge. So this is what sulfate would look like. All right, so for question 2, we need our intramolecular bond. So that's on the inside. So as you'll notice, we have sulfurs and oxygen. So I need sulfur here, and I need oxygen. So I need my periodic table to do this. I need to find mine. Okay, I found it. Okay, so for sulfur, I have 2.58. And for oxygen, I have 3.44. Okay, so to find my change of electronegativity, I'm going to take 3.44 minus 2.58. And the value that I get here is, I'm just doing this right now, 2.58. We get 0.86. So what would this be? This would be a polar covalent bond. Okay, not a polar molecule, polar bond, polar covalent bond. So 3 and 4. Okay, so the first one is our electron movement. And the next one is our dipoles. Okay, we're going to have this for this question here. Now, because oxygen is stronger, it's going to pull the electrons towards it in each direction. Because it's pulling the electrons towards it, it's going to make oxygen partially negative, and it's going to make this sulfur partially positive. Same thing here. It's going to make this oxygen partially negative. Same thing here, and same thing there. So those are my dipoles. Next, we have 5. Okay, so 5 is our Vesper shape. Okay, in order to do this, we need our lone pairs, bond pairs. And we only look at the central atom. So if I'm looking at sulfur here, I have 0 lone pairs and I have 4 bond pairs. And I know that I have 4 bonds because I have 4 oxygen atoms combined. So looking at my Vesper structure, you should have came up with the fact that this here is tetrahedral. Okay. So question 6, I'm going to just kind of go in order here. Is tetrahedral symmetrical or non-symmetrical? So looking at your structure on that Vesper structure sheet, you should have come up with the fact that this here is symmetrical. 7, like we've done before, is this a polar or a non-polar molecule? So because it's symmetrical, it's going to be non-polar. Now, question 8. What type of intermolecular force do we have? Okay. Now, your 3 options are dipole-dipole, hydrogen bond, or London dispersion. And like I said before, you only tell me the strongest one that you have. I don't want to see all 3 of them. For water, for example, I just want to see the strongest one. So in this case, because this is not polar, there's going to be no hydrogen bond, there's going to be no dipole-dipole. So the strongest one, unfortunately, is just the London dispersion. And that's how we do this here. And that's how we come up with that. Okay, so once again, in order to do this, you have to be able to draw. If you can't draw, you're not going to get any of this right, unfortunately. Okay, so it's imperative that you know how to draw these. Okay, so hopefully that made sense. All right. Now our last section. Okay, now we talk a little bit about dissolving compounds. Okay. Now, when we mix 2 compounds together, sometimes they mix and sometimes they don't. Okay. Now, for example, 2 things that I can think of is if we had, for example, oil and vinegar. Okay. If you mix oil and vinegar together, are they going to mix? No, they're not. Okay. Now, the reason why they don't mix is because oil is a non-polar compound and vinegar is polar. So those 2 do not like each other, so they're not going to mix. What about water and salt? Those are going to mix because they're both polar. Salt is an ionic compound. Okay, so NaCl is ionic, metal, non-metal. So this is 1 plus 1 negative. And water is polar. Okay, we've seen this quite a bit of times, right? So because one's polar, one's ionic, they both have charges. They're going to interact with each other. Okay, same thing here with water and vinegar. They're going to mix because they're both polar. Water's polar, vinegar's polar. Vinegar's like a little bit of an acid, so there's a little bit of polarness in it. This one's showing water and oil, and they're not going to mix because once again, water is polar, oil is not. So what we say is this here, and you'll hear this quite a bit in chemistry. Like dissolves like. A polar and polar will mix. Non-polar, okay, I just put non and non. they will mix. But if you had polar and non-polar, they will not mix. Okay? And once again, a polar compound is also an ionic compound. Polar means that you have charges. Okay? Even if they're partial charges, so like delta negative or delta positive, or if you had full charges, one positive or one negative. Okay, those are all examples of polar, all examples of charges. So they all act the same. So this is what we have here. Okay, this is the strength that we have. London dispersion is the weakest. If you have two dipole-dipoles, so if you had two things that had dipoles, that's next. If you had one dipole and one ionic bond coming together, so that's example of water with salt, right? Water is polar, salt is ionic. If you mixed water and salt together, the interactions is stronger than just having two dipoles. And then lastly, our hydrogen bond is the strongest one here. Okay? So, let's try these questions here. Which one has the higher boiling point? CH4 or H2S? So in order to do this, what we need to do is we need to actually figure out, are these compounds polar, non-polar? What do we have? So what I'm going to do is I'm actually going to do this question over here. Okay, so I have CH4 and I have H2S. Okay, so CH4, we're going to have this compound. Once again, if you're not sure how to draw, practice this, but you should know that carbon has 4, so we're going to have a compound that looks like this. Okay, H2S is actually the same as H2O. Oxygen and sulfur in the same family. So we're actually going to have a compound that looks like, almost like H2O, but instead of an O, we have an S there. Okay. Now, this here, once again, you should know how to do this. We've been doing this for a couple days now. So you should know that this here, okay, the Vesper structure is tetrahedral. Okay, this makes it symmetrical. It makes it nonpolar. Okay, so then you're only going to have London dispersion. This one here, water, once again, you guys should know this is bent. Okay, it's non-symmetrical. It's polar. And because it's polar, we're going to have our dipole-dipole. I was going to say hydrogen bond, but we don't have hydrogen bond. We would have it in water, but we don't have it in that one there. So the question's asking which one would have a higher boiling point. Now, in order to do that, you need to figure out which one of these two bonds is stronger. So which one here is stronger? Well, dipole-dipole is stronger than London dispersion. So because the dipole-dipole bond is stronger, it means that it's more compact. And because it's more compact, it's going to take more energy in the form of heat. So it's going to take a higher temperature to break up those bonds. So for question 1, H2S here would have a higher melting point. It would have a higher boiling point. It would even have a higher surface tension than the CH4. Question 2. Okay. Now, for question 2, what I want you to do is I want you to cross out these two, and we're just going to work with the same ones. We're going to put CH4 and we're going to put H2S. We're going to use the exact same one so we don't have to redraw. Okay, so for question 2, which of these compounds would dissolve in water? Now, in order to do that, you need to remember like dissolves like. So we need to figure out what is water. Okay, now once again, that one should be pretty straightforward because it's the same as H2S. We would have oxygen, 2 hydrogens. Okay, we have bent shape, bent or angular, non-symmetrical, it's polar, and it's a dipole-dipole. So, if we're looking for like dissolves like, which one here is also dipole-dipole? Same thing, it's still H2S. So H2S would dissolve with H2O. And now, once again, it's not just because it looks the same. You have to look at the actual compound, dipole-dipole. So even if you had, for example, NH3, okay, we looked at this one in a previous lesson. NH3 is also polar, okay? This one is actually a hydrogen bond. But because it's polar, because it's a polar molecule, these would also mix together as well. These will not, because one is polar, one is non-polar. So once again, like dissolves like, and that's what we have here. Okay, so thank you for watching. I hope that made sense to you, and have a great day.